Tonight, we drift into the most ancient and mysterious chapter of our universe, a time when darkness held sway over everything and nothing yet had learned to shine. We are traveling back to when the cosmos was young and silent, 13 billion years old and waiting. Long before galaxies spiraled into being, before planets gathered around smaller stars, before anything like what we see today existed anywhere in the heavens, there was a darkness so complete that even light itself had not yet been born. In this journey, we will follow the awakening of the very first stars. These were not gentle suns like ours, but monuments of fury and brilliance, brief and terrible and beautiful beyond measure. If you enjoy these quiet explorations of how the universe came to be, I invite you to like, subscribe, or share a thought below. For now, breathe with me. Let the weight of deep time settle over you. Let us begin this descent into the cosmic past. 400,000 years after the Big Bang, the universe existed in a state almost unimaginable to us now. There were no stars, no galaxies, no planets or moons. There were no rocks, no mountains, no oceans. There was only a cold, dark fog filling all of space. This fog consisted of atoms, simple, primordial atoms of hydrogen and helium, the only two elements that had yet formed from the cooling energy of creation itself. The entire universe was transparent but empty, a void filled with this thin mist. Light could travel through it, and indeed, light was there in the form of the cosmic microwave background radiation, the afterglow of the Big Bang itself. Yet this light was stretched out across vast wavelengths and spread so thin that it barely illuminated anything. The microwave background radiation was not in the visible spectrum. If your eyes could somehow detect radiation in that wavelength, you would see an almost uniform glow coming from every direction. Imagine looking through glass on the darkest night, where even starlight cannot pierce the gloom. That is what the universe was like in these early ages. The fog was not uniform. Within it, there were subtle variations, tiny differences in density and temperature that had been imprinted on the universe when it was infinitesimally small, during the moment of inflation itself. These variations were so slight that you might never notice them if you were somehow present. Yet they were there, seeds of structure waiting in the darkness, seeds that would eventually become galaxies and clusters of galaxies stretching across the cosmos. The density variations amounted to only about 1 part in 100,000. The temperature variations were similarly tiny, yet these minuscule differences would, over the course of hundreds of millions of years, grow to become the structures visible today. For hundreds of millions of years, the universe remained cold and mostly dark, save for the distant glow of that ancient radiation. It was the dark ages of the universe, a time when everything was potential and nothing was yet real. Nothing shone, nothing burned, nothing created light of its own. The cosmos waited. Into this darkness came the first atoms, each made of nothing but the simplest elements. Hydrogen made up about 75% of all ordinary matter in the universe. Helium comprised most of the rest, about 25%. These two elements had been forged in the first moments after the Big Bang, when temperatures were so extreme that protons and neutrons fused together in a brief dance of creation. This happened within the first few minutes of the Big Bang, during an epoch called Big Bang nucleosynthesis. Lithium was there too, but in such tiny quantities that it seemed almost like a whisper compared to the roar of hydrogen and helium. Only about 1 part in a billion of the universe was made of lithium. For millions and millions of years, these atoms floated in the void, lonely and scattered. They had no molecules to form, no chemistry to drive them forward. Hydrogen and helium by themselves do not easily combine. They exist as individual atoms, drifting in the expanding cosmos. The universe was still expanding, space itself was growing larger, and all the atoms were being carried apart from each other by this cosmic expansion. Imagine each atom as a single grain of sand, and the entire universe as an ocean of sand so sparse and spread out that even as far as you could see, you would encounter only a handful of grains. That is how dilute this primordial fog truly was. Yet unlike sand, these atoms had weight. They had gravity. Every single particle in the universe was pulling on every other particle with the force of gravity, an attraction that was weak beyond measure, but present nonetheless. The strength of gravity depends on both the masses involved and the distance between them. With such sparse material spread across unimaginably vast distances, the gravitational force between any two atoms was incredibly weak. Yet it never gave up. It was patient and relentless. It would shape everything that came after. Beneath this visible universe of atoms and light lay something even more mysterious and abundant: dark matter. This invisible substance filled the cosmos, 5 times more plentiful than ordinary matter, more massive than all the atoms combined, yet completely unobservable except through its gravitational effects. Dark matter does not emit light or absorb light. It does not interact with atoms the way atoms interact with each other. Yet it has gravity, and that gravity is profound. In the early universe, dark matter was not distributed evenly. It clumped together more densely in some places than others, following the same pattern of fluctuations that existed in ordinary matter. These fluctuations had been imprinted on the universe during the inflationary epoch, a period of exponential expansion that occurred fractions of a second after the Big Bang. Think of the universe as a vast cosmic web made of dark matter, with threads and knots and intersections. At each node of this invisible web, where dark matter gathered most densely, gravity pulled harder. These regions became special places in the cosmos. They became prisons of gravity, places where ordinary matter would eventually be drawn. Without dark matter's presence, the universe would have remained nearly uniform forever. Hydrogen and helium atoms would have drifted apart, moving away from each other as the universe expanded, growing ever more dilute. The density variations would have dissipated, structure would never have formed, stars would never have been born. But dark matter's gravitational pull was stronger in some places. It shaped the cosmos like an invisible hand, creating the architecture upon which all future structure would be built. The ordinary matter was drawn toward the regions where dark matter had accumulated. This process took millions of years, but was relentless. The first proto-galaxies would form at the nodes of this dark matter web, and within them, in the densest pockets of gas, the first stars would eventually ignite. In the darkness, gravity was working slowly and patiently. Where the dark matter had gathered most densely, its gravitational pull was strongest. This pull attracted the nearby hydrogen and helium gas, drawing it inward. As more gas was drawn together, the gravity became even stronger, creating a feedback loop. Material accumulated toward the center, and the concentration of matter increased. Over millions of years, clouds of gas began to form. These were not small clouds like you might see on Earth. These were proto-galaxies, cosmic structures that would eventually become the first galaxies. They were small by cosmic standards, perhaps 30 to 100 light-years across, but enormous by any human measure. Each proto-galaxy contained vast amounts of hydrogen and helium, billions of times more material than exists in our entire solar system. Imagine the density of such structures. Start with a cloud of gas so thin and diffuse that no earthly instrument could detect it. Spread it across a region of space 30 light-years across. That's still incredibly sparse. Yet it contains more material than 1 billion solar systems. This gives some sense of the scales involved in the early universe. Within these proto-galaxies, the gas was not distributed evenly. Denser regions formed within the larger clouds, pockets where material had accumulated more heavily. Gravity continued to pull inward in these dense pockets, gathering the gas tighter and tighter. The process was relentless. The denser the gas became, the stronger the gravitational attraction. The stronger the attraction, the faster the gas fell inward. Over time, these regions would become sites where the first stars would form. They were not yet stars. They were simply concentrations of gas, collapsing under their own weight, pulled together by gravity into increasing, dense clumps. The collapse was inexorable and slow, but it was happening across the universe in countless locations simultaneously. In some protogalaxies, multiple sites of collapse formed. In others, a single massive core dominated the gravitational landscape. Either way, the collapse was occurring. The universe was organizing itself, drawing matter together from the vast diffuse medium of the early cosmos. As the gas clouds collapsed under gravity, something crucial happened. The temperature and pressure within them rose. This is the same principle that makes a bicycle pump warm when you compress air inside it. As the gas was pushed together into a smaller and smaller volume, its atoms moved faster and faster, colliding with each other more frequently and with greater force. The temperature climbed steadily. At first, it was still cold by any earthly standard, perhaps 10 or 20 degrees above absolute zero. But in the context of the early universe, this was tremendously hot. The density inside these collapsing clouds increased alongside the temperature. Where once the gas had been spread out and diffuse, it now began to concentrate. The atoms that had drifted so freely began to press again, against each other, creating pressures that became significant. As the density increased, more atoms occupied the same space, which meant more gravity was being generated by the mass that was present. This created another feedback loop. Higher density meant stronger gravity, which pulled more material inward, which increased the density further. The process accelerated as the eons passed. In some regions, the collapse slowed or even halted temporarily, held back by the pressure of the heated gas resisting gravity's pull. But gravity was relentless. It could not be stopped forever. The pressure could slow the collapse but never entirely prevent it. The temperature inside these cores eventually climbed to thousands of degrees Kelvin, then tens of thousands, then hundreds of thousands. The atoms inside were moving at relativistic speeds, approaching the speed of light. As the gas clouds continued to collapse, this process accelerated. The temperature climbed higher and higher. The pressure mounted. Eventually, after millions of years of collapse, conditions began to reach the critical threshold where something extraordinary would happen. The first cores were approaching the moment of ignition, the moment when temperatures would reach the critical point for hydrogen fusion to begin. Within these dense, hot cores, the first stars would be born, but only when the conditions were right. Only when the collapse had proceeded far enough and the temperatures had climbed high enough. At that moment, a new era would begin. The first stars to form in the universe were known to astronomers as population 3 stars, or POP3 stars. These were fundamentally different from any stars we observe today. They were made entirely of hydrogen and helium, with only trace amounts of lithium. There were no heavier elements, no carbon or nitrogen or oxygen, no iron or silicon, or any of the metals that we think of as essential to star formation and planetary science. Population 3 stars were composed purely of the primordial elements, the materials left over directly from the Big Bang itself. This composition was not accidental or incidental. It was the defining characteristic of these ancient objects. The first generation of stars had formed from gas that had never before been inside a star. It was pristine, untouched by any stellar nucleosynthesis or cosmic alchemy. No supernova had ever enriched it. No stellar wind had ever carried heavy elements into it. For billions of years before the first stars ignited, the hydrogen and helium in the universe had simply drifted through space, accumulating in gravitational wells, waiting. When stars finally did form, these initial suns had no choice but to be made from what was available: pure hydrogen and helium, and virtually nothing else. This absence of heavier elements had profound consequences for how these stars formed and how they behaved. The absence of metals meant that the gas could not cool as efficiently as modern gas clouds cool. Metals are excellent at radiating heat away. Even tiny amounts of carbon or iron or other heavy elements can dramatically increase the cooling efficiency of a gas cloud. They help gas clouds fragment into smaller pieces. Without metals, this cooling was much less effective, which meant that the gas clouds could not break up into small fragments as easily as they do today. The cooling timescale for primordial gas was vastly longer than for modern gas enriched with metals. This meant that during the collapse, the gas heated up more before it could radiate that heat away. The first stars were massive beyond imagination. While our sun has a mass of 1, the first stars had masses of dozens, hundreds, even up to 1,000 times the mass of our sun. An individual population 3 star might have weighed as much as 100 solar masses, or even more. Some estimates suggest that the very first stars could have massed up to 1,000 times what our sun weighs. To put this in perspective, 100 solar masses means a star equivalent to the mass of 100 million Earths. It is difficult for the human mind to comprehend such scales. These were not gentle, modest stars like ours. These were monuments of gravity and pressure and heat, objects so enormous that they could only exist for the briefest moments in cosmic time. The luminosity of such massive stars was correspondingly enormous. A star with 100 times the mass of our sun is not 100 times brighter. It is vastly brighter due to the physics of stellar interiors. More massive stars have hotter cores, higher fusion rates, and greater luminosities. 100 solar mass star might be millions of times brighter than our sun. The massive nature of these stars was a direct consequence of the absence of metals in the primordial gas. When a gas cloud wants to collapse under gravity and form a star, it needs to cool down. Cooling allows the cloud to contract to smaller and smaller volumes without the pressure building up so much that it stops the collapse. In modern gas clouds, metals provide this cooling. They radiate away heat efficiently, allowing fragmentation into smaller clumps. But the primordial gas had no metals. Molecular hydrogen was the only cooling agent available, and it was far less efficient. Without adequate cooling, the gas could not fragment into small pieces. Instead, entire regions of gas had to collapse together, forming single massive objects. The collapse was inevitable. Gravity pulled harder than cooling could resist, so massive stars had to form. There was no way around it. The first stellar generation had to be extraordinarily massive. The Jeans mass, a quantity that represents the minimum mass needed for gravitational collapse to occur in a given gas cloud, was much higher for primordial gas than for modern gas. This meant that when portions of the cloud became dense enough to collapse, they already contained enormous amounts of material. Small stars could not form under these conditions. Only massive stars could be born. The absence of heavier elements meant something profound. The early universe was chemically pure in a way that would never come again. Every atom in a population 3 star was either hydrogen or helium, nothing more. There were no carbon atoms, no nitrogen, no oxygen. There was no iron or nickel or silicon. There were no rocky materials at all. Chemistry as we know it did not exist. The periodic table of elements that we are familiar with today was, in the universe of the first stars, still almost entirely absent. Only 2 elements existed in any significant quantity. This limitation seems almost impossible to us now, but it was the reality of the time. The star could not have planets orbiting it, at least not rocky planets like Earth or Mars or Venus. It could not have the complex chemistry that eventually leads to life. Life requires carbon and nitrogen and oxygen and countless other elements. Without those elements, life as we know it could not possibly exist. The star could not have the diversity of elements that makes the modern universe such a rich and complicated place. All of that was still in the future. For now, in these first population 3 stars, there was only the most basic simplicity imaginable. Hydrogen and helium, and the tiniest trace of lithium. That was all there was. These stars burned purely on hydrogen fusion. In the core, hydrogen atoms fused together to form helium, releasing energy in the process. This was the only nuclear reaction that could occur, because there were no other elements present to fuse. There was no carbon cycle, no CNO cycle that occurs in more massive modern stars. There was no triple alpha process that produces carbon in older stars. There was only the proton-proton chain, the simplest form of hydrogen fusion. The stars burned their hydrogen with an intensity that would be unimaginable if we could witness it. They were brilliant beyond measure, shining with a light that had never been seen before in the entire history of the universe. Deep within the collapsing gas clouds, temperatures rose toward the ignition point. For millions of years, the collapse continued. The density at the center of each dense core climbed higher and higher. The temperature soared. The pressure mounted to levels that would be considered incomprehensibly extreme by any terrestrial standard. The gas at the core was no longer gas in any conventional sense. It had become a quark-gluon plasma, a state of matter more fundamental than atoms, where quarks and gluons moved freely. Finally, after eons of gravitational collapse, something extraordinary happened. The temperature at the center of the core reached approximately 10 million degrees Kelvin. At this critical temperature, the protons of hydrogen atoms began to fuse together. The thermal energy was sufficient to overcome the Coulomb barrier, the electrical repulsion between two positively charged protons. Two protons came close enough that the strong nuclear force overcame their mutual electrical repulsion. They fused, forming deuterium, a heavy isotope of hydrogen. This process released energy in the form of light and heat and neutrinos. The energy flowed outward from the core, pushing against the surrounding gas and halting the collapse. The outward pressure from the energy being released balanced the inward pull of gravity. Hydrostatic equilibrium had been achieved. The star had found its stable configuration. A star had been born. For the first time in the history of the universe, nuclear fusion was happening. For the first time, a star was shining with its own light. The darkness that had reigned supreme for hundreds of millions of years was finally being broken. The light spreading outward from that first star was the first starlight ever to exist. It was blue and brilliant and hot beyond measure. The energy released by hydrogen fusion in that first stellar core was absolutely staggering. In the core, millions of tons of hydrogen were being converted to helium every second. Each conversion released energy according to Einstein's equation, E equals mc squared. Small amounts of mass were being transformed directly into tremendous amounts of energy. This energy flowed outward as radiation, as particles, as neutrinos. Imagine being there in that ancient cosmos, surrounded by darkness, and then suddenly a point of brilliant light appears. That is what must have happened when the first star ignited. The universe that had been silent and dark for hundreds of millions of years suddenly erupted with light. This light traveled outward in all directions, illuminating the surrounding gas clouds. The radiation filled the region around the star, beginning the process of ionization that would eventually spread throughout the universe. The universe would never be the same again. And then another star ignited, and another. Within the dense gas clouds that made up the early protogalaxies, many cores had formed. As one core reached critical temperature and began to fuse, the energy it released began to influence its surroundings. Some of this energy helped trigger the collapse of nearby cores, and they too began to form stars. The compression from the radiation and stellar winds of newly formed stars could actually compress nearby gas, helping to trigger additional collapse. Throughout the universe, in countless locations simultaneously, the first stars were beginning to shine. They were not arranged in any particular order or pattern. They formed where the gas was densest, where gravity had pulled hardest. In some regions, many stars formed close together, creating loose stellar clusters. In other regions, stars formed more sparsely. Each star burned its hydrogen intensely, shining with a light that radiated outward in all directions. These were not red dwarfs or yellow suns. These were massive, hot, blue stars. The color of a star depends on its temperature. Hotter stars are blue, cooler stars are red. Population 3 stars were so hot that they shone with a brilliant blue light. The surface temperature of a population 3 star could be hundreds of thousands of degrees, or even more. Population 3 stars were so hot and so luminous that they produced an enormous amount of ultraviolet radiation. This ultraviolet light was significant because it carried tremendous energy. When this light encountered the neutral hydrogen gas that surrounded the stars, something began to happen. The ultraviolet photons struck the hydrogen atoms and knocked the electrons free from the protons. This process was called ionization. The energy required to ionize a hydrogen atom is 13.6 electron volts, and ultraviolet photons carry far more energy than this. A single photon could ionize a hydrogen atom and still have energy left over. Some of this excess energy went into making the freed electron move faster, giving it kinetic energy. This process happened continuously throughout the regions around the stars, as the stream of ultraviolet photons from the stellar surface struck the surrounding gas. The ionized gas began to glow, emitting its own light as electrons recombined with protons and released energy in the process. The heat of these tremendous stars was matched only by their brevity. Because population 3 stars were so massive, they burned their hydrogen at an incredible rate. The more massive a star is, the faster it consumes its fuel. Our Sun will live for approximately 10 billion years. A population 3 star, with a mass of 100 times our Sun or more, had a lifespan measured in millions of years, not billions. Some of the most massive population 3 stars might have lived only a few million years before reaching the end of their lives. This is an incredibly short time on cosmic scales. It is a blink of an eye in the history of a universe that is 13 billion years old. Yet in that brief span, they transformed their surroundings forever. Ours were, in a sense, in a constant rush. They were burning through their fuel at such prodigious rates that they could not afford to do anything except shine. They converted hydrogen to helium in their cores at a pace so intense that nothing could slow them down. The pressure and temperature in their cores remained at the highest levels imaginable. These conditions could not be sustained for long. The core of a population 3 star was a place of unimaginable violence. The temperature there was so extreme that the hydrogen atoms were stripped of their electrons completely, existing only as bare protons and neutrons bouncing around in a relativistic plasma. The density was extraordinary, with matter packed so tightly that the mass of the entire Earth would fit into a volume the size of a grain of sand. Yet even in this extreme environment, the fundamental rules of physics applied. Pressure increased with density, and pressure increased with temperature. As the star aged and consumed its hydrogen fuel, it was constantly in a race against itself. The very act of burning fuel and releasing energy held back the catastrophic collapse of gravity. If the fusion reaction had suddenly ceased, the whole star would have collapsed in upon itself within seconds. Nothing could have stopped it. The gravitational force pulling inward would have overwhelmed any obstacle, but the fusion continued relentlessly, pouring energy outward, maintaining the precarious balance. For millions of years, this delicate equilibrium held. Eventually, though, it would not. That end, when it came, would be violent and transformative beyond anything the universe had yet experienced. The radiation pouring out from these massive stars was not like the gentle sunlight that warms the Earth. It was fierce and intense and carried tremendous energy. The pressure from this radiation was significant enough to push against the surrounding gas. In regions very close to the stars, the radiation pressure became strong enough to blow the surrounding material away from the star itself. This created what are called stellar winds, streams of gas being driven outward by the intense radiation. These winds could be quite violent, with material streaming away from the star at speeds of thousands of kilometers per second. The stellar winds carved out regions around the stars that were relatively empty of gas. They swept away the material that might have otherwise continued to collapse and form more stars. In this way, the radiation from the first stars began to regulate how much gas could remain in the surrounding regions. The radiation and the winds created a negative feedback, a process that slowed or halted the formation of additional stars in regions close to the massive ones. The ultraviolet radiation was particularly important. When a photon of ultraviolet light struck a neutral hydrogen atom, it could knock the electron loose. This happened because ultraviolet photons carried more energy than lower frequency light. A single ultraviolet photon could ionize an atom if its energy exceeded the ionization potential of that atom. For hydrogen, this threshold was 13.6 electron volts. Population 3 stars were hot enough that a significant fraction of the light they emitted was in the ultraviolet range. This meant that vast quantities of ionizing photons were streaming outward from each star in all directions. The region immediately around each star became increasingly ionized. The ultraviolet radiation could travel through space over significant distances before being absorbed. When it encountered neutral hydrogen atoms, it ionized them, stripping away their electrons. This process happened throughout the volumes of gas surrounding the stars, creating spherical regions where the hydrogen was no longer neutral but ionized. Around each massive population 3 star, a bubble of ionized gas began to expand. The ultraviolet radiation from the star ionized all the neutral hydrogen within a certain distance. The ionized gas, being made up of loose protons and electrons, behaved differently than neutral gas. It was less dense in some ways and more energetic in others. These bubbles of ionized gas expanded outward, pushing against the surrounding neutral material. The boundary of the bubble, the interface between ionized and neutral gas, was a region of intense activity. The ionized gas on the inside was hot and energetic. The neutral gas on the outside was cooler and denser. This difference in properties meant that there was a sharp transition between the two regions. The expanding ionization front pushed outward at a steady pace, driven by the continuous stream of ultraviolet photons from the star. As more and more first stars formed and began to shine, more and more bubbles appeared. These bubbles grew larger over time. Eventually, bubbles from different stars began to overlap and merge. Where two bubbles touched, they expanded into each other, creating larger regions of ionized gas. Over millions of years, these bubbles of ionization began to overlap across regions of the universe, filling more and more of the space that had previously been filled with neutral hydrogen. The boundaries between the bubbles collapsed inward, allowing the ionized regions to merge. What had been isolated spheres became irregular shapes and then large connected regions. The process accelerated. As more stars formed, more ionizing radiation was produced. The ionization fronts moved faster and faster. The neutral hydrogen that had filled the universe for hundreds of millions of years was being replaced by ionized plasma. Electrons and protons were being separated, creating a sea of charged particles. This process was the beginning of cosmic reionization, the most dramatic transformation the universe had undergone since the first moments after the Big Bang itself. The universe was transitioning from neutral to ionized, from dark to illuminated, from a realm where light could travel freely to a realm where light was constantly interacting with charged particles and being scattered and absorbed. The first stars had done this. Their light had rewritten the very nature of the cosmos. What had been shadow was becoming light. And as they died, they transformed everything. After only a few million years of burning so intensely, the cores of these massive population 3 stars began to falter. The hydrogen fuel was exhausted. The fusion reactions that had held back gravity's relentless pull were finally beginning to slow. What happened next was inevitable and catastrophic. The star's inner structure began to collapse inward. The core, which had been held up by the outward pressure of fusion, suddenly had nothing to support it. Gravity overwhelmed the outward force. The collapse happened quickly, in just minutes or hours for the largest stars. The material fell inward at tremendous speed, accelerated by the gravitational pull of all the surrounding layers pressing down from above. As the core collapsed, it became denser and denser, hotter and hotter. The temperatures climbed into the billions of degrees. The electrons were forced into the protons, creating neutrons. The density became so extreme that it is almost impossible to comprehend. A volume the size of a grain of sand would weigh as much as a mountain. The collapse continued until the core reached densities so high that the strong nuclear force itself could barely hold the matter together. Then something extraordinary happened. The collapse stopped. The infalling material slammed into the core with such force that it rebounded outward in a massive shockwave. This shockwave tore through the outer layers of the star with unimaginable violence. It was a supernova, the violent death of a star. The explosion released more energy in a few seconds than our sun will release in its entire 10 billion year lifetime. The outer layers of the star were blown outward at speeds of 30,000 kilometers per second or more. The light from the explosion would be visible across the entire observable universe if anyone had been there to see it. But there was no one. There were no observers yet. There were no galaxies to look up at the sky. There were only the stars themselves and the darkness. They were slowly beginning to illuminate. The explosion continued for hours and days, spreading outward, ionizing the surrounding gas, heating it to billions of degrees. Waves of radiation rippled outward, traveling at the speed of light, illuminating everything in their path. The star that had seemed so eternal and permanent was suddenly gone, torn apart and scattered into space. Yet something crucial happened in that moment of destruction. Something that would forever change the universe. Inside the core of that dying population 3 star, something happened that had never occurred before. The temperature and pressure inside the collapsing core became so extreme that entirely new nuclear reactions began to occur. In the crushing depths of the core, before the shockwave blew through it, for just a moment, the conditions were right for something remarkable. The temperature soared past billions of degrees, reaching levels that had never been seen anywhere in the cosmos. Iron nuclei began to fuse together. Carbon and oxygen fused into heavier elements. Silicon fused into iron. Each reaction released energy, but also drove the temperature higher, enabling even heavier fusion reactions. In that brief moment before destruction, the core of the star became a factory for the creation of new elements that had never existed before anywhere in the universe. Carbon was created, the element that would eventually make up the bodies of every living thing. Nitrogen was created from the fusion of carbon and helium. Oxygen was created from multiple pathways of nuclear synthesis. Iron, silicon, magnesium, sulfur, and dozens of other elements that we think of as fundamental to chemistry and life were all created inside this dying star. The process is called nucleosynthesis, the birth of new elements through nuclear fusion. It happened not in the slow, steady burning of the star's normal lifetime, but in the frantic, violent moments of its death. The temperatures and pressures during core collapse allow fusion reactions that never occur during normal stellar burning. New elements are born in a burst of creation. These elements were not born as free atoms. They existed as atomic nuclei, packed together so tightly that they could barely exist. But when the shockwave blew through, the whole core was torn apart. The newly created elements were flung outward at tremendous speeds, carried away from the dying star on waves of expanding material. They were scattered into the surrounding gas, mingling with the hydrogen and helium that had always been there. For the first time, the cosmos contained elements heavier than helium and lithium. For the first time, the universe had been enriched with metals. This was only the beginning. But not all massive stars died in the same way. Some population 3 stars were even more massive than the ones that created supernova explosions. These were truly gigantic objects, weighing hundreds or even 1,000 times as much as our Sun. For these monsters, the death was different and even more violent. As these ultramassive stars aged and consumed their hydrogen, they began to build up heavier and heavier elements in their cores. Eventually, the cores became so massive that they could not be held up even by the pressure of normal fusion. Something catastrophic occurred. Instead of collapsing gradually and rebounding as a normal supernova, these cores entered a different regime entirely. The density and temperature became so extreme that something happened that defies normal stellar physics. The photons produced by the heat began to create particle-antiparticle pairs, primarily electrons and positrons. As temperature climbed, more and more of the photon energy was converted into these pairs. The photons began to carry less and less of the outward pressure that held up the star. The pressure from radiation declined just as gravity reached its peak strength. There was nothing to hold up the core anymore. The collapse became catastrophic. The electrons and positrons created at such extreme temperatures annihilated each other, converting their mass back to energy, which only made things worse. The core collapsed without any resistance. The entire star became unstable. The entire outer envelope of the star, all the way to the surface, became part of the collapse. The entire star fell inward together. Then, in an instant, the entire mass of the star from the center to the surface was completely ejected into space at velocities that reached light speed itself. This was a pair instability supernova, and it was the most violent explosion that nature could produce. The entire star was obliterated. No core remained. Nothing was left behind. The star ceased to exist entirely. The explosion released energy equivalent to 100 normal supernovae. It created more heavy elements than 1,000 smaller stars. Iron, nickel, cobalt, and other elements were scattered through the cosmos. The light from such an explosion could be seen across the universe if observers existed to see it. But the most important consequence was not the light. It was the heavy elements. The metals that were scattered outward would eventually become the building blocks for planets, for dust, for all the chemistry that would eventually lead to life itself. Yet even these extraordinary explosions were not the only way population 3 stars died. Some of the most massive stars did not explode at all. As they approached the end of their lives, their cores became so massive that they collapsed entirely. The entire star fell inward, crushing the core beyond the density even of a neutron star. The core did not rebound. No shockwave tore through the outer layers. Instead, the collapse continued unimpeded, faster and faster, until the core reached a density so extreme that even light could not escape it. A black hole was born. The formation of black holes from the death of population 3 stars had profound implications for the early universe. Black holes are regions of space where gravity is so strong that nothing can escape, not even light itself. They form when a massive star collapses and its core becomes compressed to an impossibly dense point called a singularity. The density at a singularity is so extreme that our normal understanding of physics breaks down. Around the singularity is an event horizon, a spherical boundary beyond which no light can travel. It is the point of no return. Once anything crosses the event horizon, it cannot escape, no matter how fast it travels. These black holes were the first black holes to form in the universe. They were not the ultramassive black holes we see at the centers of galaxies today, weighing millions of times more than the Sun. They were smaller, stellar mass black holes, created by the direct collapse of massive population 3-star cores. Yet they represented something extraordinary. They were windows into physics at its most extreme. They were laboratories where the fabric of space-time itself was warped and twisted by gravity in ways never before seen in the cosmos. They were objects that would eventually play a role in shaping the universe through their accretion of surrounding material and their influence on the surrounding gas. The most significant consequence of these black holes was more subtle. As population 3 stars throughout the universe reached the end of their lives and collapsed, some of them left behind black holes. These black holes were not distributed uniformly throughout space. They were concentrated in the regions where the first stars had formed, which were the nodes of the dark matter web. Multiple black holes could have formed in the same small region, in the same proto-galaxy. When black holes are close together, they can merge. Two black holes in orbit around each other gradually lose energy to gravitational waves, spiraling inward and eventually colliding. When they merge, a larger black hole results. In the dense stellar clusters of the early universe, this process could happen repeatedly. A black hole formed from one population 3 star might merge with a black hole from another, creating a larger object. This larger black hole might then merge with another, creating something even bigger. Over millions of years, this merger process could build up black holes of increasing mass. The smallest seed black holes, those formed from direct collapse of individual population 3 stars, might have weighed only a few solar masses. But through repeated mergers, they could grow to 10 times the mass of the Sun, then 100 times, then more. These hierarchical mergers created a ladder of black hole masses, with larger and larger objects forming from the collision of smaller ones. This process might have created some of the intermediate mass black holes observed in the universe today, but more importantly, it provided a pathway to something far more extreme. The most massive black holes that live at the centers of galaxies weigh millions or even billions of solar masses. How could such objects form in such a young universe? The answer might lie in these mergers of population 3 era black holes. The seed black holes from population 3 stars, grown through hierarchical merging, could have eventually become the seeds for supermassive black holes. They would grow larger through accretion of surrounding material and through continued merging. Over time, they would evolve into the supermassive black holes seen in modern galaxies. Yet this process takes time, and observations show that supermassive black holes existed less than 1 billion years after the Big Bang. The presence of these extremely early supermassive black holes suggests that population 3 stars must have died and created black holes very early in cosmic history, just as the theory predicts. Today, astronomers cannot see population 3 stars directly. They are long gone, vanished billions of years ago into history. Yet we can see their legacy written in the chemistry of stars that exist today. Certain stars in our galaxy, particularly old stars in the galactic halo and in nearby dwarf galaxies, have extraordinarily low metal content. These stars formed from gas that had been enriched by only 1 or 2 population 3 supernovae. The metal content of these ancient stars is measured by comparing the abundance of heavy elements to the abundance of iron. Astronomers use the notation to denote this ratio relative to the Sun. The Sun has equal to 0 by definition. Stars with equal to -5 have 100,000th the iron to hydrogen ratio of the Sun. Stars with equal to -7 have about 1/10,000,000th the iron abundance. These extraordinarily metal-poor stars are fossils of the early universe, relics preserved from an ancient era. They preserve in their atmospheres the elemental signatures of the supernovae that enriched the gas from which they formed. If a star formed from gas enriched by a single population 3 supernova, its composition will reflect the elements that particular supernova created. Some population 3 supernovae create more iron, others create more oxygen or silicon. By studying the compositions of metal-poor stars, astronomers can work backward and infer what population 3 supernovae must have been like. The metal-poor stars become time capsules, preserving information about the first stars and their deaths. The most metal-poor stars known are almost unimaginably ancient and rare. One star in particular, designated SMSS J03136708, has been measured to have less than -7. This star contains less than a millionth of the iron-to-hydrogen ratio of the Sun. In absolute terms, this star might contain only a few million kilograms of iron in its entire mass, compared to millions of billions of kilograms of hydrogen. The composition of this star suggests that it formed from gas enriched by only a single population 3 supernova, or possibly from the tail end of enrichment by such a supernova. This star is a direct descendant of the first stars, separated by more than 13 billion years, but carrying their signature deep in its elemental composition. Studying such stars allows us to probe the nature of the first generation of stars indirectly, learning about population 3 through these ancient descendants. In the universe as a whole, the effect of all these population 3 supernovae was transformative. Billions of stars, each creating heavy elements, each scattering those elements into the surrounding gas. The metals accumulated, the abundance of heavy elements in the cosmos increased. The universe became richer chemically with each passing million years. This metal enrichment had immediate consequences. The metals, even in small quantities, fundamentally altered how future stars would form. Remember that population 3 stars were so massive because the primordial gas could not cool efficiently. Metals are excellent coolants. They absorb thermal energy and radiate it away as light. When even a small amount of metal is introduced into a gas cloud, the cooling efficiency increases dramatically. The gas can now lose heat more readily, allowing it to collapse to smaller and smaller sizes. The Jeans mass, the minimum mass required for gravitational collapse, decreases. Where once only massive stars could form, now smaller stars became possible. The universe began a transition from population 3 to population 2. Population 2 stars were still much more massive than modern stars, but they were smaller than the population 3 giants. They lived longer, burning their fuel at a more measured pace. They were not as bright as population 3 stars, but there could be more of them. As the metal abundance increased, the characteristic mass of newly formed stars decreased. The universe began to produce a more diverse array of stellar types. It was the beginning of a cosmic transition from the era of monster stars to an era of more varied stellar populations. As the light from population 3 stars continued to pour outward in all directions, it transformed the universe itself. The ultraviolet radiation from these massive hot stars was the most potent ionizing force in the cosmos. When an ultraviolet photon struck a neutral hydrogen atom, it knocked the electron free with tremendous force. The atom became ionized, splitting into a free proton and a free electron, where before the universe had been filled with neutral hydrogen atoms. Now there were regions of ionized gas, regions where the electrons and protons moved independently. These regions grew outward from each star-like expanding bubbles. The boundary of each bubble was an ionization front, a sharp transition between neutral hydrogen outside and ionized hydrogen inside. The temperature jumped sharply at this boundary, from cool neutral gas to hot ionized gas. As time passed, these bubbles expanded outward. The radius of each bubble grew larger year after year. The ultraviolet radiation had to travel through the increasingly ionized gas. But ionized gas does not absorb ultraviolet photons the way neutral hydrogen does. Instead, the light passed through, continuing outward until it encountered neutral hydrogen further out and caused more ionization. The bubbles grew larger and larger, expanding at a steady pace driven by the continuous stream of ionizing photons. Eventually, bubbles from different stars began to overlap. Where two bubbles touched, they began to merge. The ionized regions connected together, forming larger and larger zones of ionized gas that covered vast regions. The neutral hydrogen that had filled the universe was being replaced. Across regions millions of light-years across, the gas transitioned from neutral to ionized. This process would eventually be called cosmic reionization. It was one of the most fundamental transformations in the history of the universe. It marked the end of the cosmic dark ages and the beginning of a new era where the universe glowed with radiation. The transition from neutral to ionized was not instantaneous. It took millions of years. The first stars formed at a redshift of around 30, meaning the universe was only about 200 million years old. The universe was not fully reionized until a redshift of around 6, when the universe was about 1 billion years old. So for roughly 800 million years, the universe was in a state of partial reionization, with some regions ionized by starlight and other regions still neutral. This transition era, called the Epoch of Reionization, was a time of dramatic change. The density of ionized regions increased over time. The neutral regions shrank. Eventually, the ionized regions dominated, and the universe became predominantly ionized. The light from the early stars made this possible. Without the ultraviolet radiation from population 3 and population 2 stars, the universe would have remained neutral. The density of ionized gas would never have risen significantly. The universe would have remained a cold, mostly dark place, filled with neutral hydrogen waiting to form the first galaxies. The stars changed all of that. Their light ionized the universe and made it transparent to radiation in new ways. As the universe became increasingly ionized, the structure of matter changed in fundamental ways. Before reionization, the neutral gas could cool through radiation from hydrogen atoms and molecules. After reionization, the gas was hot, ionized, and more resistant to collapse. The pressure increased dramatically. The ionized gas pushed outward more strongly than the neutral gas had. Regions of dense material could still collapse to form structures, but the process became more difficult. The ionization front moving outward from the first stars created zones of hot, ionized gas. Inside these zones, the pressure was higher, making it harder for the gas to collapse and form new stars. But at the boundaries, at the transition regions between ionized and neutral gas, something different happened. The pressure differences created instabilities. The gas piled up at the boundaries. Density enhancements formed. These density enhancements could gravitationally attract more material, forming denser concentrations. The boundaries between ionized regions became sites of active structure formation. Galaxies began to form at these boundaries. The ionization process itself, rather than inhibiting galaxy formation, actually triggered it in some regions. The expanding ionization fronts compressed the neutral gas at their edges, squeezing it into denser concentrations that could then collapse gravitationally and form galaxies. Within the densest regions of the early universe, where dark matter had accumulated most strongly, the first true clusters of stars were forming. These were not the isolated massive population 3 stars that had formed first. These were true clusters, dense groupings of hundreds or thousands of stars formed together in the same region of space. The clusters formed because the gas in these dense regions became increasingly fragmented. While a single massive population 3 star had formed from a large cloud of gas that could not fragment due to poor cooling, as metals were added and the cooling efficiency improved, the same cloud of gas could now break into smaller pieces. The gas no longer needed to form one giant star. Instead, it could cool more efficiently and break apart. Each piece could collapse and form a star. Instead of one massive star forming from a cloud, dozens or hundreds of smaller stars could form from the same total amount of gas. Stellar clusters were born. These clusters were not stable for long. The stars in them were moving at random velocities, not organized into neat orbits. Some stars would be moving faster than others, traveling with velocities of many kilometers per second through the cluster. Gradually, the faster-moving stars would escape the cluster, traveling off into space due to their higher speeds. The cluster would evaporate, its stars dispersing into the surrounding volume of space over millions of years. But while the cluster existed, even temporarily, it was a site of intense activity. The stars shone brightly together. The radiation from hundreds of stars combined created extremely intense ultraviolet fields. These fields ionized the surrounding gas even more effectively than a single massive star could, creating larger and more rapid ionization fronts. Young stellar clusters became engines of ionization in the early universe. As these stellar clusters and isolated stars accumulated in the dense regions of the early universe, they began to form the seeds of the first galaxies. A galaxy is fundamentally a system of stars held together by gravity. The first proto-galaxies, the regions where stars were beginning to accumulate, were not yet true galaxies in the modern sense. They were messy, chaotic collections of stars and gas and dark matter. But they had the essential property of galaxies. They were systems bound together by gravity. The dark matter in these regions provided the gravitational scaffolding. Stars formed in the densest pockets of this dark matter. As more stars formed, they added to the total mass of the system, increasing the gravity and making it easier to retain additional stars and gas. The proto-galaxies grew. Stars were added one by one, or in small clusters. The structure became richer and more complex. The ionizing radiation from the stars began to heat the surrounding gas, but some of that gas was still being pulled inward by gravity. The gas that fell into the system contributed to its growth. Over millions of years, the proto-galaxies grew into larger structures. They accumulated thousands, then millions of stars. The first true galaxies were being born. Yet the process was far from smooth or orderly. The radiation from the stars had profound effects on the formation of new stars. The ultraviolet photons ionized the gas, heating it. Hot gas resists collapse. The pressure support from the heat pushes outward against gravity. In regions close to massive stars, the radiation was so intense that it completely prevented new star formation. The gas was ionized, heated, and blown outward, but in regions slightly farther away, where the radiation was less intense, the gas was heated but not completely dispersed. The boundaries of the ionized regions became sites of active star formation. The compressed gas at these boundaries could collapse and form new stars. The stars already present were thus regulating the formation of future stars. They were creating a feedback loop. The massive population 3 and early population 2 stars could be thought of as hostile to new star formation in their immediate surroundings. But paradoxically, their radiation also compressed the gas at larger distances, triggering new star formation there. The universe was a complex system of competing processes. As we look back at the early universe from our vantage point in the modern cosmos, we see these ancient objects indirectly through the observations of the James Webb Space Telescope. JWST is the most powerful astronomical observatory ever built, a marvel of engineering and precision optics. It observes the universe in the infrared, allowing it to see through dust and to detect very faint, very distant objects. When JWST looks at the early universe, it is seeing galaxies as they were more than 13 billion years ago, close to the edge of the observable universe. The light from these distant galaxies has been traveling through space for more than 13 billion years to reach us. By the time it arrives, it has been stretched and redshifted by the expansion of the universe. The wavelengths become longer, shifting from visible light toward the infrared. JWST's infrared detectors can detect this faint, redshifted light with remarkable sensitivity. The telescope can resolve details in these ancient galaxies that would be impossible to see in visible light. JWST can measure the brightness of the galaxies at different wavelengths, creating a spectrum. The spectrum carries information about the composition of the stars, the age of the galaxy, and the rate at which new stars are being formed. For the first time in human history, we have an instrument capable of actually seeing the epoch of reionization and the first galaxies that formed during it. The light from galaxies at a redshift of 8 or 9, meaning they formed only about 600 million years after the Big Bang, is just becoming visible to JWST observations. These are remarkably early galaxies, yet they show evidence of already containing significant numbers of stars. One particular galaxy has become especially important in the search for population 3 stars. This is the galaxy LAP-1b, located more than 13 billion light-years away. The light we see from this galaxy today left it 800 million years after the Big Bang. LAP-1b is not exceptionally bright or large. Without special techniques, even JWST could not see it clearly. But this galaxy is located behind a massive galaxy cluster. The gravity of the cluster acts like a lens, magnifying the light from LAP-1b, making it appear much brighter and larger than it would be otherwise. This phenomenon, called gravitational lensing, was predicted by Einstein's theory of general relativity more than a century ago. The massive gravity of the galaxy cluster warps space-time, bending the light rays from the distant galaxy. The light is magnified by a factor of more than 100. With this magnification, JWST can see details in LAP-1b that would otherwise be impossible to detect. When astronomers analyzed the spectrum of LAP-1b, they found something remarkable and exciting. The spectrum showed emission lines characteristic of very hot, massive stars. The pattern of emission lines was exactly what theoretical models predicted for a population of population 3 stars. The stars appeared to be extraordinarily massive, each weighing more than 100 times the mass of our Sun. This is exactly the mass range predicted for population 3 stars by decades of theoretical work. The light from LP-1b appears to come from a young cluster of massive stars, possibly population 3 stars that formed very early in the galaxy's history. If confirmed, this would represent the first direct detection of population 3 stars. Another promising candidate is the galaxy GNZ11, one of the most distant galaxies known, with light that left it only about 430 million years after the Big Bang. Recent analysis of GNZ11 with JWST has revealed a faint signal in the outer regions of the galaxy that is consistent with extremely massive young stars. The signal suggests the presence of very luminous objects, more luminous than expected for normal galaxies at this epoch. The properties match predictions for population 3 stars. The detection is tentative, and confirmation will require additional observations. But the possibility is tantalizing. We may be looking at the very first generation of stars, the objects that first illuminated the universe. Each new observation with JWST brings us closer to confirming the existence of population 3 stars and understanding their true properties. The epoch of the first stars is finally becoming accessible to direct observation. After more than a century of astronomical history, the dream of seeing the first stars is coming within reach. The universe's earliest chapter is opening before our eyes. Perfect! I've completed the script for part 3 of the first stars that ever lit the universe. The draft is 4,998 words, which falls within the target range of 4,750, 250 words, 5,000 plus or minus 5% than we might expect. The problem lies not in the theoretical understanding, but in the practical limitations of observing objects so distant and so faint that their light barely registers on even the most sensitive instruments. When we look back toward the cosmic dawn, we are not simply looking at distance, we are looking through time itself. The light we receive from the most distant galaxies has traveled for more than 13 billion years to reach Earth. During that journey, the universe has not stood still. It has continued to expand, stretching space itself. This expansion has a profound effect on the light traveling through it. The wavelengths of the light get stretched as space expands. A photon that left a distant star as blue ultraviolet light gets shifted toward longer wavelength, S, becoming red, then infrared, then further into the infrared spectrum. This effect is called redshift, named for the way light gets shifted toward the red end of the spectrum. The redshift is measured as a dimensionless number called Z. A Z-value of 0 means the light has not been shifted at all, meaning it comes from nearby. A Z-value of 1 means the light has been stretched by a factor of 2. A Z-value of 3 means it has been stretched by a factor of 4. The most distant galaxies known have Z-values greater than 20, meaning their light has been stretched by factors of 20 to 30 or more. The relationship between Z and distance is not linear in our expanding universe. The geometry of space-time itself changes this relationship. A galaxy with Z equal to 1 is not Twick, E, as far as a galaxy with Z equal to 0. Instead, it is much farther. The look-back time is also not linear. A galaxy at Z equal to 1 is not seen as it was halfway through the universe's history. Instead, it is seen as it was much earlier. JWST observes galaxies at Z values around 15 to 20, meaning it looks back to times when the universe was only a few 100 million years old. The light from such galaxies has been redshifted so much that it now arrives in the infrared, exactly the wavelengths that JWST was designed to detect. The redshift tells us the distance and the look-back time, but it also tells us something profound about the universe's expansion history. The rate of expansion has changed over cosmic time. In the early universe, gravity dominated, pulling material together and slowing expansion. In the modern universe, dark energy dominates, accelerating expansion. By measuring the redshifts of many galaxies at different distances, astronomers can map out the expansion history of the universe itself. The measurements have revealed that the expansion accelerated about 5 billion years ago, a discovery that earned Nobel Prize recognition. This has led to revolutionary discoveries about dark energy and the ultimate fate of the cosmos. The universe appears to be expanding faster and faster, driven by some mysterious form of energy that fills all of space. But for our purposes, redshift is the tool that lets us see back to the epoch when the first stars were forming. Without understanding redshift, we could never determine the true distance to these ancient objects, or their actual luminosity. Redshift is the key to unlocking the early universe's secrets. Yet redshift is not the only way astronomers can probe the early universe. There is another signal, far more subtle, that carries information about the cosmic dark ages and the era when the first stars began to form. This signal comes from the behavior of hydrogen gas itself. Hydrogen atoms possess a peculiar property. The electron can occupy different energy states around the nucleus. The lowest energy state is called the ground state. The electron can also be in excited states, where it orbits at a greater distance from the nucleus. When an electron transitions from a higher energy state to the ground state, it releases energy as a photon. The energy released depends on which states are involved in the transition. One particular transition is extraordinarily important for studying the early universe. It occurs when the electron flips its spin while remaining in the ground state. The electron has an intrinsic angular momentum called spin. It can spin in one direction, creating a state with slightly higher energy, or it can spin in the opposite direction, creating the ground state with lower energy. When the electron flips from the higher spin state to the lower spin state, it releases a photon with a very specific wavelength. That wavelength is 21 centimeters. This emission is called the 21 centimeter line, or the hydrogen line. It is one of the most important signals in radio astronomy. The 21 centimeter line is important for studying the early universe because neutral hydrogen gas in the interstellar medium absorbs and emits radiation at this wavelength. When radiation from a bright source passes through a cloud of neutral hydrogen, the hydrogen absorbs photons at a 21 centimeter wavelength, creating a dark line in the spectrum. The intensity of this absorption tells us how much neutral hydrogen is present along the line of sight. The line appears dark against the bright background because the foreground gas has removed photons from the beam. In the early universe, the gas was predominantly neutral before reionization occurred. The 21 centimeter line could reveal the distribution of neutral hydrogen during the Dark Ages and the epoch of reionization. As the first stars formed and their ultraviolet light ionized the surrounding gas, the neutral hydrogen disappeared, replaced by ionized hydrogen. The 21 centimeter absorption signal would weaken as the fraction of ionized gas increased. By observing the 21 centimeter line from galaxies at different redshifts, astronomers can see how the neutral hydrogen abundance changed over time. They can detect the epoch of reionization by observing when the 21 centimeter signal becomes weak or vanishes entirely. Current radio telescopes can detect the 21 centimeter line from nearby objects with remarkable clarity, but detecting it from the early universe has proven extraordinarily difficult. The signal is extremely faint because it comes from such distant sources. The signal strength drops with distance squared, following the inverse square law. New radio telescopes currently under construction, such as the Square Kilometre Array, will have sufficient sensitivity to detect the 21 centimeter line from the epoch of reionization. These observations will revolutionize our understanding of when and how the first stars ionized the universe. The SKA will map the distribution of neutral hydrogen during the epoch of reionization with unprecedented detail. Understanding the epoch of reionization requires more than just observation. It requires simulation. The physics involved is extraordinarily complex. Gravity pulls gas together. The gas heats up. Stars form. The stars emit radiation. The radiation ionizes the gas. The ionized gas becomes hot and resists collapse. The pressure from the hot ionized gas affects where new stars can form. All these processes happen simultaneously, interacting with each other in intricate ways. No theoretical equation can be solved by hand to predict the outcome. Instead, cosmologists use supercomputers to simulate the process. These simulations divide the early universe into a grid of small cells. Each cell contains some dark matter, some ordinary matter, and possibly some stars. The physics within each cell is calculated according to the laws of gravity, thermodynamics, and radiative transfer. The simulations track how the density, temperature, composition, and radiation field change in each cell over time. The cells are connected to neighboring cells, allowing information to flow between them. The calculations proceed in small time steps, advancing the simulation forward. Each time step requires billions of calculations. A full simulation of cosmic reionization covering a volume large enough to capture the statistical properties of the universe might require 1 trillion time steps or more. Even with modern supercomputers capable of performing petaflops of calculations per second, such simulations can take months to complete. The simulations have revealed surprising details about the epoch of reionization. It was not a uniform process. It did not happen simultaneously everywhere. Instead, ionization began around the first massive stars and spread outward. The first ionization fronts expanded as bubbles of ionized gas surrounded the most luminous stars. These bubbles grew and eventually overlapped with bubbles from other stars. The overlap regions connected the ionized zones, forming larger and larger regions of ionized gas. Eventually, the ionized regions filled most of the universe, and only small remnants of neutral hydrogen survived in the densest regions deep within massive galaxy clusters. The simulations show that this process took hundreds of millions of years. The first stars began ionizing the universe at a redshift of around 30. The universe was not fully reionized until a redshift of around 6. During the transition, there were times when more than half the universe remained neutral, coexisting with regions of ionized gas. The epoch of reionization was a time of great complexity and inhomogeneity. Different regions ionized at different times. Some regions ionized early due to abundant massive stars. Other regions remained neutral for longer because fewer stars had formed there. The simulations reveal a patchwork universe with ionized regions gradually expanding and merging together until they covered everything. The seeds of structure that would eventually grow into stars and galaxies came from subtle density variations present at the very beginning. When the universe was extremely young, quantum fluctuations in the primordial field were stretched to cosmic scales by inflation. These fluctuations created regions that were slightly denser than average and regions that were slightly less dense. After inflation, the universe expanded, but these density variations persisted. They were imprinted on both the ordinary matter and the dark matter. In the aftermath of the Big Bang, the universe was nearly perfectly uniform. The density variations were incredibly small. In the densest regions, the matter density might be 1% higher than average. In the least dense regions, it might be 1% lower. These tiny variations seem insignificant, yet they were the seeds from which all cosmic structure eventually grew. Gravity amplified these variations. In regions slightly denser than average, gravity was slightly stronger. The extra gravity pulled in more material, making those regions even denser. This runaway process continued over billions of years, transforming the small initial variations into the enormous structures we see today. The galaxies and galaxy clusters that fill the universe. The cosmic microwave background radiation carries a record of these original density variations. Regions of higher density were slightly hotter when the radiation decoupled from matter. The radiation from hotter regions has slightly higher energy, appearing bluer. The radiation from cooler regions has slightly lower energy, appearing redder. By mapping the tiny temperature variations in the cosmic microwave background, astronomers have measured the spectrum of density fluctuations present at the very beginning of time. The temperature variations in the CMB are only about 1 part in 100,000, yet they represent the density variations that seeded everything. The density fluctuations that grew into the first stars and galaxies had a characteristic scale determined by the physics of the early universe. Before recombination, the photons in the cosmic microwave background were tightly coupled to the ordinary matter. They exerted radiation pressure that resisted gravitational collapse. The pressure and gravity created acoustic oscillations, standing waves in the density of matter. These acoustic waves had a characteristic wavelength called the sound horizon. After recombination, when the photons decoupled from the matter, the radiation pressure disappeared. The acoustic oscillations stopped, freezing the density pattern into place. The size of the features in this frozen pattern was set by the sound horizon. The distance sound could travel before recombination. This sound horizon scale imprinted itself on the distribution of galaxies. Galaxies tend to be separated by distances corresponding to this scale. The baryon acoustic oscillations, as these features are called, appear in the large-scale distribution of galaxies and in the power spectrum of density fluctuations. By measuring the baryon acoustic oscillations in galaxy surveys, astronomers have determined the size of the sound horizon and thus the geometry and composition of the universe. This technique has become one of the most powerful methods for measuring cosmic distances and testing theories of cosmic expansion. The baryon acoustic oscillations leave an imprint on every large galaxy survey. They appear as peaks in the correlation function that measures how likely two galaxies are to be found at a specific separation. The location of these peaks tells us about the cosmic expansion history. Future galaxy surveys will measure the baryon acoustic oscillations with even greater precision. allowing astronomers to test dark energy theories in unprecedented detail. When the first dense regions began to collapse under gravity, the gas within them had to cool. If the gas remained hot, thermal pressure would prevent further collapse. The gas would heat up as it fell inward, and the increasing pressure would resist the inward pull of gravity. Only if the gas could cool, radiating away the heat generated by gravitational compression, could the collapse continue. In the early universe, the primary coolant was molecular hydrogen. Hydrogen atoms could combine to form H2 molecules. These molecules could absorb thermal energy through rotational and vibrational excitations. The molecules would then emit radiation, carrying that energy away. This cooling allowed the gas to collapse. But molecular hydrogen had limitations. It is difficult to form. The reaction of hydrogen atoms combining to form H2 requires 3 particles to collide simultaneously. Such three-body collisions are rare in dilute gas. The probability of such events decreases rapidly as the gas becomes more dilute. Molecular hydrogen could form more readily in the densest regions, but it was always a trace constituent of the gas, perhaps 1 in a billion atoms. Even with molecular hydrogen cooling, the minimum temperature to which the gas could cool was about 300 Kelvin. This limited cooling meant that the gene's mass, the minimum mass for gravitational collapse, remained very large. The gene's mass is the critical threshold where gravitational force overcomes pressure. Only clouds with masses exceeding 1 million solar masses could collapse efficiently. Smaller clouds would heat up before they could collapse to the point of star formation. This is why the first stars were so massive. They formed from the largest possible collapsing regions, with no smaller companions. The universe's initial stellar population was dominated by giant suns. The cooling efficiency improved dramatically when metals became abundant. Metals are extremely effective coolants. Elements like carbon, nitrogen, oxygen, silicon, and iron have many possible energy states. Electrons in atoms of these elements can be excited to higher energy states by collisions with other particles. When the electrons transition back to lower energy states, they emit radiation across a broad spectrum of wavelengths. This allows the gas to lose heat efficiently at many different temperatures, from very high to very low. Forbidden line transitions, where the normal selection rules are violated, allow atoms to radiate energy even at very low densities. When the metallicity of the gas rises above about 1,000th of the solar value, the metals dominate the cooling. The gas can cool to temperatures lower than even the cosmic microwave background radiation temperature. The cooling becomes efficient enough that gravitational collapse can proceed without heating the gas. The gene's mass drops dramatically. Instead of requiring millions solar mass clouds to form stars, clouds of 100,000 solar masses can now form stars. Eventually, as the metallicity increases further, clouds of thousands of solar masses can form stars. At solar metallicity, star-forming clouds can fragment into clouds of tens of solar masses. The composition of the collapsing cloud determines the mass of the stars that form from it. This relationship between metallicity and stellar mass explains the progression from population 3 stars to population 2 to population I stars, like our sun. Each generation of stars enrich the cosmos with metals, allowing the next generation to be smaller and more abundant. The change in stellar masses reflected the change in cooling efficiency. The first molecules to form in the universe were simple diatomic molecules. Hydrogen combined with hydrogen to form H2. Helium was inert and did not readily combine with anything. As metals became more abundant, more complex molecules could form. Carbon could bond with hydrogen to form molecules like CH and CH2. Carbon could bond with nitrogen to form CN. Carbon, nitrogen, and oxygen bonded together in countless combinations. Methane, ammonia, and more complex hydrocarbons formed. Silicon formed SiO and other compounds. As the universe aged, the chemistry became richer. Molecules that would eventually be important for life, like water and organic compounds, were being synthesized in the high-temperature, high-pressure environments of stellar interiors and in the expanding remnants of supernovae. The detection of these molecules in the early universe has been possible through spectroscopy. When light from distant objects passes through gas containing these molecules, the molecules absorb light at specific wavelengths corresponding to their energy transitions. The wavelengths depend on the molecular structure. By observing the absorption lines in the spectra of distant galaxies and quasars, astronomers can determine which molecules are present in the early universe. Surprisingly, molecules have been detected in galaxies that formed only a few 100 million years after the Big Bang. This indicates that the chemical enrichment proceeded rapidly, faster than many models predicted. The universe was not only forming stars, but also becoming chemically complex very quickly. Whether the first stars formed as single isolated objects or as multiple stars in a system depends on how the collapsing gas cloud fragmented. If a collapsing cloud remained as a single coherent entity throughout its collapse, it would form a single star. But if the cloud fragmented into smaller pieces, each piece could collapse into its own star. Fragmentation depends on the cooling efficiency and the angular momentum of the cloud. If the cloud can cool efficiently, it can fragment into many pieces. If the cloud rotates rapidly, centrifugal force inhibits fragmentation. In the early universe, the poor cooling efficiency of primordial gas inhibited fragmentation. The single collapsing cloud could not break apart easily. The density and temperature would rise uniformly throughout the cloud, preventing the formation of separate collapse regions. This led to the formation of single massive stars from entire million solar mass clouds. But current theoretical models indicate that even without efficient cooling, some fragmentation can occur in the accretion disks that form around the protostars. As material falls onto the forming star, it accumulates in a disk. The disk becomes progressively larger and more massive as material from the envelope continues to feed into it. The disk can become unstable if it is massive enough relative to the central star. Gravitational instabilities can develop in the disk, where the self-gravity of the disk material becomes important. The instability can cause the disk to fragment into multiple pieces, each of which can collapse into its own star. The result is a multiple star system, with two or more stars orbiting a common center of mass. Such binary or multiple star systems could have formed in the early universe from the fragmentation of disk-like structures. The radiation from a forming massive star does not come only from the fusion of hydrogen in the core. In fact, during the formation process, before the star reaches the main sequence where steady hydrogen fusion occurs, the primary source of radiation is gravitational energy from accretion. As material falls onto the surface of the forming star, it gains kinetic energy from gravity. When it impacts the surface, this kinetic energy is converted to heat. The star's surface becomes extremely hot and radiates away the energy that is continually being added by the infalling material. For a massive protostar, this accretion luminosity can be tremendous. A star of 100 solar masses with a high accretion rate might emit as much light as millions of suns. The temperature at the star's surface can exceed 10,000 Kelvin, causing it to shine with intense blue-white light. This enormous luminosity creates a radiation pressure that acts on the infalling material. The radiation pushes outward against the inward pull of gravity. For the highest mass stars with the highest accretion rates, the radiation pressure can become strong enough to oppose the infalling material. The accretion can be slowed or even halted by the radiation pressure. This creates a fundamental limit on how massive a star can become. The Eddington limit defines the maximum mass for a star. Stars more massive than the Eddington limit cannot form because radiation pressure prevents further accretion. This limit depends on the composition of the star and the opacity of the material falling onto its surface. In the early universe, with primordial composition, the Eddington limit may have been somewhat different from modern calculations. The question of when the first stars formed is central to understanding the early universe. Observations with JWST and other telescopes have pushed back the evidence for galaxy formation and star formation to times earlier than previously thought possible. Galaxies detected at redshifts greater than 15 were not expected by many models, yet they are present. This suggests that star formation must have begun even earlier. Current evidence suggests that the first stars began to form at redshifts greater than 30, possibly as early as redshift 40 or higher. This corresponds to times only 200 million years after the Big Bang, or even earlier. At these extreme redshifts, the universe was very different from the modern universe. The density was much higher. The first structures were just beginning to assemble. The conditions were ripe for the formation of the first stars. Once the first stars began to form, the process accelerated. As the universe expanded, more and more dark matter accumulated in increasingly massive halos. Each time a dark matter halo reached a sufficient mass, gas could begin to cool within it, allowing stars to form. The star formation rate increased with time as more and more halos reached the critical threshold for star formation. By a redshift of around 20, when the universe was only about 170 million years old, significant populations of stars were forming throughout the universe. The universe had transformed from being nearly empty to having stars in many different locations. The transition from a starless universe to a universe filled with stars happened remarkably quickly in cosmic terms. The era of population 3 stars did not last indefinitely. These massive stars, with lifetimes of only a few million years, rapidly consumed their hydrogen fuel. The most massive stars burned out within just a few million years. Within 50 to 100 million years of the first stars forming, most of the earliest generation had already died in supernovae. The metals they produced began to accumulate in the interstellar gas. The enrichment proceeded faster in the densest regions, where the stellar mass density was highest and the supernova rate was highest. As the metallicity increased, the cooling efficiency improved. New stars forming from the enriched gas were smaller. The stellar mass function, the distribution of stellar masses among newborn stars, shifted toward lower masses. Population of massive population 3 stars was gradually replaced by a population of smaller population 2 stars. The transition was not instantaneous. For a time, both massive population 3 stars and smaller population 2 stars were forming in the same regions, competing for the available gas. The oldest stars in our galaxy show this transition. The most metal-poor stars we can observe today, with metallicities less than 1/10,000,000th of the solar value, are population 2 stars that formed early in the transition. They contain the signature of having been enriched by only a single population 3 supernova. These ancient stars are fossils that preserve information about the very first generation. Their chemical composition tells a story about how the first stars shaped the universe. The chemical evolution of the universe proceeded along a specific pathway. It began with the primordial elements, hydrogen, helium, and trace lithium, produced in the Big Bang nucleosynthesis. The first stars, population 3, were formed entirely from this primordial material. These stars synthesized the first heavy elements in their cores and ejected them into space through stellar winds and supernovae. The abundance of heavy elements increased. The second generation of stars, population 2, formed from gas enriched by population 3 supernovae. These stars synthesized additional heavy elements and added them to the interstellar gas. The enrichment continued. With each generation, the metals accumulated, the cooling improved, and the stellar masses decreased. Current stars like our Sun, E-population I stars, formed from gas enriched by billions of years of stellar evolution. The Sun contains about 2% heavy elements by mass. This enrichment history is preserved in the elemental abundances of stars. By measuring the abundance ratios of different elements in a star's atmosphere, astronomers can determine how many nucleosynthesis events contributed to that star's formation. A star with an abundance pattern showing high ratios of certain elements to iron likely formed from gas enriched by only a few population 3 supernovae. The pattern of abundance ratios serves as a chemical fossil. Different elements are produced in different amounts depending on the type of supernova and the mass of the progenitor star. Iron is produced copiously in iron core collapse supernovae. Oxygen is produced especially in more massive progenitors. These distinctive patterns allow astronomers to read the nucleosynthesis history encoded in a star's composition. The globular clusters scattered throughout our galaxy carry ancient memories of the early universe. These dense aggregates of hundreds of thousands or millions of stars formed very early in galactic history. Some globular clusters have ages approaching 13 billion years, nearly as old as the universe itself. The stars within globular clusters are predominantly old, low-mass stars. The more massive stars have already died and can no longer be observed. Yet globular clusters provide crucial evidence about star formation in the early universe. The metal content of globular clusters varies widely. Some clusters are metal-rich, while others are so metal-poor that they must have formed very early, from gas enriched by only a few supernovae. The color magnitude diagram of globular clusters, a plot of stellar brightness versus color, reveals the age and composition of the cluster. The shape of the main sequence, where most stars lie, is determined by stellar masses, ages, and compositions. By fitting models to the observed color magnitude diagrams, astronomers can determine when the clusters formed with reasonable accuracy. The oldest clusters appear to have formed less than 1 billion years after the Big Bang. This means significant star formation must have occurred in the very early universe. Globular clusters serve as time capsules from the early universe, preserving in their stellar populations a record of ancient star formation. The cosmic microwave background radiation carries information about the universe at a very early time, just 380,000 years after the Big Bang. At that epoch, the universe was not yet filled with stars. The CMB was emitted at a time before any stars had formed. Yet the CMB contains information about the universe's composition and the density fluctuations that would eventually grow into galaxies and stars. The power spectrum of temperature fluctuations in the CMB reveals the amplitude of density fluctuations at different scales. The data show that the universe was extraordinarily smooth, with density variations of only about 1 part in 100,000. These tiny variations grew over billions of years due to gravitational instability, eventually becoming the galaxies we observe today. The CMB also carries information about the baryon density, the density of ordinary matter composed of protons and neutrons. By fitting models to the CMB power spectrum, astronomers have determined that ordinary matter makes up about 5% of the total energy content of the universe. The remaining 95% is dark matter and dark energy. The measurement of the baryon density from the CMB has profound implications for understanding star formation. With a known baryon density and a known dark matter density, the total mass of the universe can be calculated. This allows predictions about how many dark matter halos should exist and thus how many galaxies should form. The predictions can then be compared with actual observations of galaxy populations at various redshifts. Good agreement between predictions and observations validates the standard cosmological model. The merger of black holes in the early universe produces gravitational waves, ripples in space-time itself. When two black holes orbit each other, they gradually lose orbital energy by radiating gravitational waves. Over time, the orbits decay. The two black holes spiral inward, moving faster and faster. Eventually, they collide and merge, forming a larger black hole. During the final moments of merger, when the black holes are moving at a significant fraction of the speed of light, the gravitational wave intensity becomes enormous. The merger itself releases a pulse of gravitational waves with tremendous amplitude. These gravitational waves travel outward at the speed of light, carrying information about the black hole masses and spins. The first gravitational wave detection in 2015 came from the merger of two stellar mass black holes of about 30 solar masses each. The detection was revolutionary, proving that gravitational waves exist and opening a new window on the universe. Since then, hundreds of gravitational wave events have been detected. Some of the black holes detected have masses larger than the most massive stellar remnants can explain. These might be intermediate mass black holes, or the result of multiple mergers. The detection of such massive black holes suggests that the growth of black holes through hierarchical merging might be more efficient than previously thought. In the early universe, where the density was higher, black hole mergers might have been even more common. The gravitational waves from these mergers carry information about the physics of the early universe and the growth of black holes in the first billion years after the Big Bang. The formation of dust grains in the early universe represented another crucial transition, one that often goes unnoticed in discussions of the first stars. Yet dust fundamentally altered how the universe would evolve. When massive population 3 stars exploded as supernovae, they did more than just scatter metals into the intergalactic medium. The intense heat and pressure of the explosion created conditions where dust could form. Silicates and carbon compounds condensed from the cooling ejector, creating the first solid grains, microscopic particles of cosmic dust. These grains were extraordinarily small, perhaps a fraction of a micrometer across, yet they were profoundly significant. Dust absorbs and scatters light. It absorbs ultraviolet radiation and re-emits that energy as infrared radiation. In the early universe, even tiny amounts of dust could significantly alter how light traveled through space. The presence of dust affected how we observed distant objects. It dimmed their light. It reddened their light by preferentially absorbing shorter blue wavelengths while allowing longer red wavelengths to pass through. The earliest dust-forming supernovae released copious amounts of dust into the surrounding gas. Within a few 100 million years of the first stars forming, dust had become commonplace throughout certain regions of the early universe. This dust would eventually become incorporated into new stars and planets that formed in subsequent generations. It provided surfaces where complex chemistry could occur, allowing molecules to form more readily. It altered temperatures in collapsing clouds by changing how efficiently radiation could escape. It changed how stars formed by modifying the fundamental cooling and heating balance in the primordial gas. The dust grains were literally the building blocks of subsequent cosmic structures, the seeds from which galaxies would eventually construct their stellar populations. Infrared signatures reveal the presence of the first stars even when visible light cannot penetrate the surrounding material. The light from the earliest stars is often obscured by intervening dust and gas clouds. The ultraviolet light they emit gets absorbed by dust grains and re-radiated as infrared radiation. This infrared light, with its longer wavelengths, can travel through dust clouds that would be completely opaque to visible light. The James Webb Space Telescope was specifically designed to detect infrared radiation across multiple wavelength bands. Its primary mirror is cooled to cryogenic temperatures to minimize the infrared radiation emitted by the telescope itself, which would otherwise completely drown out the faint signals from distant galaxies. The infrared signatures of first stars appear in very specific patterns that encode information about their properties. The spectra of starlight absorbed and re-emitted by dust show distinctive characteristic features. Dust surrounding hot massive stars absorbs ultraviolet and visible light and re-emits it as infrared radiation. The re-emitted radiation peaks at wavelengths determined by the temperature of the dust grains. Hot dust emits in the near-infrared, around a few micrometers wavelength. Cooler dust emits in the far infrared at tens of micrometers or longer wavelengths. By analyzing the infrared spectrum in detail, astronomers can determine the temperature of the dust and the amount of energy being radiated into space. They can estimate the stellar luminosity from the total infrared output. The presence of infrared excess, more infrared light than would be expected from the stellar spectrum alone, clearly indicates dust. The amount of infrared excess directly relates to the amount and distribution of dust. Studying these infrared properties reveals not only that stars exist in these distant galaxies, but also tells us about the dust surrounding them and its properties. The detailed characteristics of the infrared light tells us about the stellar populations that are heating the dust, whether the stars are hot and massive or cooler and smaller, whether they are young and still actively embedded in surrounding gas, or older and more exposed to the interstellar medium. Lyman alpha emission provides another crucial signature for detecting the first stars and galaxies in the early universe. Lyman alpha is the emission line produced by hydrogen atoms when their electrons transition from the first excited state down to the ground state. This transition releases a photon with a very specific wavelength of 121.6 nanometers in the ultraviolet part of the electromagnetic spectrum. Massive stars are particularly prolific producers of Lyman alpha photons because they emit intense ultraviolet radiation. When the ultraviolet light ionizes neutral hydrogen atoms surrounding the stars, those atoms subsequently recombine and emit Lyman alpha radiation. Many galaxies in the early universe appear as Lyman alpha emitters, with most of their detectable light concentrated in this single distinctive emission line. The Lyman alpha emission is so remarkably bright from certain galaxies that it can be detected even at enormous distances across the cosmos. However, Lyman alpha photons face a significant challenge in traveling through the universe. Neutral hydrogen gas in the intergalactic medium absorbs Lyman alpha photons very efficiently. A single Lyman alpha photon traveling through neutral hydrogen is likely to be absorbed almost immediately upon encountering the gas. The photon gets absorbed by a hydrogen atom, exciting an electron to the first excited state. When the electron falls back down, it emits another Lyman alpha photon, but this photon travels in a random direction, not necessarily continuing toward the distant observer. This scattering process means that Lyman alpha photons from distant sources are preferentially scattered and absorbed, making distant Lyman alpha sources harder to detect. Only when the intergalactic medium becomes ionized, a transformation driven by the first stars, does Lyman alpha radiation travel freely across cosmic distances. The Lyman alpha escape fraction, the proportion of Lyman alpha photons that successfully escape the galaxy without being absorbed, depends sensitively on the neutral hydrogen content of the surrounding environment and the overall structure of the galaxy. The cosmic web emerged as dark matter, and gas accumulated along the filaments connecting cosmic structures throughout space. The universe was not a uniform distribution of matter. Instead, gravity created a distinctive pattern where some regions became overdense and others became underdense. Along the boundaries between these regions, matter accumulated in elongated structures called filaments. These filaments connected dense regions called nodes or knots, where the overdensity was greatest. The resulting pattern resembled a three-dimensional cosmic web, with dense nodes connected by thinner filaments, separated by vast empty voids. The first galaxies and stars formed preferentially in these dense regions where gravity was strongest. The nodes of the cosmic web had significantly higher density, which meant gravity was stronger, making gravitational collapse and star formation more likely. The filaments also harbored star formation, though at lower rates than the nodes. The first population 3 stars formed in the dense centers of dark matter halos that occupied the nodes of the cosmic web. As the universe aged, these initial structures merged and grew, following the hierarchical structure formation process established by cosmological theory. Small dark matter halos merge to create progressively larger halos. Smaller galaxies merge to create larger galaxies. The cosmic web grew more pronounced over time, with structures becoming increasingly organized and more massive. The pattern of galaxy distribution observed in the modern universe reflects the underlying structure of the cosmic web that was established in the early universe by the distribution of dark matter. Different stellar masses led to different fates, and the initial mass function of population 3 stars determined the properties of the early universe. The most massive population 3 stars, those exceeding 100 solar masses, had the shortest lifetimes, measured in just a few million years. Their fate was a catastrophic core collapse supernova or a pair instability supernova that completely disrupted the star. The explosion was so energetic that it briefly outshone entire galaxies. These supernovae produced copious amounts of metals and ejected them at extreme velocities, often exceeding 10,000 kilometers per second. The kinetic energy in the ejector was tremendous, capable of heating the surrounding gas and even expelling it from the host galaxy. Somewhat less massive populate, on 3 stars, perhaps 50 solar masses or so, had slightly longer lifetimes, 10 to 20 million years. They ended their lives in core collapse supernovae that were nearly as energetic as the most massive objects. The iron cores of these stars collapsed to form black holes or neutron stars. The infiling material rebounded off the iron core and blasted outward, creating the explosion. The metal yield from these explosions was still substantial. Lower mass population 3 stars, perhaps 20 solar masses, lived somewhat longer, though still only tens of millions of years. They too ended in core collapse supernovae, though the energy output was somewhat less than the most massive progenitors. The metal yields from these objects were still significant enough to enrich the surrounding gas. Rotation and magnetic fields played important roles in determining how massive the first stars could grow and how long they would live. Most stars rotate to some degree, spinning on their axes. Massive population 3 stars likely rotated quite rapidly due to the nature of their formation. As a collapsing gas cloud contracted under gravity, any initial rotation would be amplified, similar to how a spinning ice skater spins faster as they pull in their arms. The rotation creates centrifugal force that acts outward, directly opposing gravity. In extremely massive stars, the rotation can become so rapid that it approaches the breakup velocity, the speed at which material at the stellar equator would be flung into space. This limiting velocity depends on the surface gravity and the internal structure of the star. Rapid rotation affects how the star evolves throughout its lifetime. It affects the transport of angular momentum and chemical elements within the star, changing internal circulation patterns. It affects the stellar wind, the stream of particles ejected from the stellar surface, making the wind denser and more structured. Magnetic fields in the early universe stars would have been extraordinarily strong. Magnetic fields arise from the motion of electrically conducting fluids like plasma. As the early stars formed, any initial magnetic field present in the collapsing gas cloud would be amplified by compression. The freezing in of magnetic field lines means the field strength increases as the conducting material is compressed. In the cores of massive stars, magnetic field strengths could reach millions of Gauss or even higher values. These remarkably strong magnetic fields would channel the stellar wind, directing the outflow along the magnetic field lines. The stellar wind carries away angular momentum, allowing the star to slow its rotation over time. Without magnetic field channeling, the rotation would continue to increase until the star became dynamically unstable. The magnetic field also affects the stellar dynamo, the mechanism by which magnetic fields are generated and maintained within the star. The complex interaction of magnetic fields with stellar radiation and mass loss shapes how the star's energy is transported and radiated into the surrounding space. The first planets could not have formed in the early universe because the conditions necessary for planetary formation simply did not exist anywhere. Planets form from the disk of dust and gas surrounding a young star. The dust in the disk gradually collects through gravitational attraction and collision into larger and larger bodies over time. Eventually, kilometer-sized objects called planetesimals form and begin to interact gravitationally. The planetesimals collide and merge, building planetary cores progressively. If a planetary core reaches sufficient mass before the disk dissipates, it can accrete a substantial atmosphere of hydrogen and helium, forming a gas giant. If the core is smaller, or if the disk is dissipated by the stellar wind or radiation, the planet remains terrestrial. For planets to form, two essential ingredients are absolutely required. First, the disk must contain substantial amounts of dust and rocky material. Second, the disk must be cool enough and long-lived enough for the slow process of planetary growth to proceed over millions of years. The early universe lacked both essential components. The early population 3 stars were so extraordinarily massive that their lifetimes were only millions of years. Planetary formation typically takes at least tens of millions of years and often requires hundreds of millions of years to complete successfully. The first stars died before planets could form around them. Additionally, even if planets managed somehow to form, they would be extremely different from planets in the modern universe. They would be composed almost entirely of hydrogen and helium, with virtually no heavy elements like carbon, silicon, or iron that form the bulk of terrestrial planets. They would lack organic molecules entirely. Life as we know it requires heavy elements and complex chemistry. The early universe offered neither essential requirement. The first environments truly suitable for planet formation arose much later, around population 2 stars that had benefited from enrichment by population 3 supernovae. X-ray emissions revealed the violent processes occurring in the early universe as massive stars shone brightly and supernovae exploded. Massive hot stars emit significant amounts of X-ray radiation as a byproduct of their high temperature and intense stellar winds. The stellar wind, a stream of hot gas flowing from the star's surface, is not smooth. It is unstable and develops turbulence. In the turbulent wind, material moving at different speeds collides, creating shock fronts. The shocked gas is heated to extremely high temperatures, millions of Kelvin. Hot gas at such extreme temperatures emits X-rays. A single massive population 3 star could produce X-ray luminosity equivalent to millions of modern suns. The X-rays travel freely through the early universe, ionizing the hydrogen gas they encounter. X-rays are energetic enough to ionize hydrogen atoms directly, a process called photoionization. A single X-ray photon can ionize a hydrogen atom, leaving behind a free proton and electron. The ionized hydrogen then absorbs X-rays less efficiently than N-neutral hydrogen. This feedback effect means that X-rays from massive stars can propagate quite far through the surrounding gas before being absorbed. The X-rays create expanding bubbles of ionized gas around massive stars. Within these bubbles, the gas is ionized and hot, unable to cool and collapse into new stars. Just outside the bubble, the ionization front marks a sharp transition from ionized to neutral gas. The expanding ionization front compresses the neutral gas just beyond it, potentially triggering gravitational instability and new star formation. The X-ray luminosities of the early universe were enormous. The most massive stars emitted X-rays at prodigious rates. The cumulative X-ray output from all the first stars significantly heated the intergalactic medium. Heating the intergalactic medium was perhaps the most transformative effect of the first stars, altering the physical state of matter throughout the universe. Before the first stars formed, the intergalactic medium was cold, only a few hundred Kelvin. The universe was mostly neutral hydrogen with trace helium. The gravitational instability that led to structure formation was only weakly opposed by thermal pressure from the cool gas. When the first stars began to shine, their radiation and stellar winds injected tremendous amounts of energy into this cool medium. Ultraviolet radiation ionized hydrogen atoms, creating ionized hydrogen plasma. X-rays from massive stars heated the gas to thousands of Kelvin or higher. Supernovae released tremendous kinetic energy in their ejector, creating shock. K-waves that plowed through the surrounding medium and heated it severely. The ionized gas is more transparent to radiation than neutral gas, allowing radiation from stars to penetrate farther. The heating increased the pressure, making it harder for gas to collapse under gravity. Regions with strong heating became stabilized against collapse. New star formation in these regions became suppressed. In regions farther from sources of heating, where the medium remained cool, gravitational collapse could still proceed more readily. The competition between heating by stars and cooling by radiation created a complex patchwork universe, where some regions were actively forming stars, while others remained quiescent. The heating of the intergalactic medium had profound implications for the structure formation that followed. It set the minimum mass scale for dark matter halos, capable of retaining gas and forming stars. It created barriers to the accretion of gas onto growing galaxies. The reheating of the intergalactic medium by the first stars was a crucial step in transforming the universe from a simple, nearly uniform medium into the complex, structured cosmos we observe. Photons escaping from the first galaxies carried the light that transformed the universe from dark to luminous. Inside the densest regions where stars formed, ionizing photons from massive stars ionized the surrounding hydrogen. These ionized regions are called Hi2 regions, regions of ionized hydrogen. The ionizing photons were produced copiously by massive young stars. The ionizing photons spread outward in expanding bubbles, ionizing hydrogen as they went. Just at the edge of each bubble, at the ionization front, the radiation intensity decreased sharply. Beyond the ionization front lay neutral hydrogen, absorbing the radiation and remaining neutral. As galaxies grew and accumulated more stars, their ionizing photon production increased. The Hi2 regions within galaxies expanded and merged. Eventually, the Hti regions from neighboring galaxies overlapped and merged together. The ionization fronts from separate sources met in the space between galaxies. When the ionization fronts met and merged, they created a continuous region of ionized gas spanning across space from one source to another. The ionized gas in these merged regions was no longer able to absorb the ionizing photons. The radiation could travel freely through ionized hydrogen. As the ionized regions expanded and merged, they grew to encompass larger and larger volumes of space. The universe underwent what is called percolation, a phase transition where isolated regions suddenly connect into a single interconnected network. This process was not instantaneous. Different regions ionized at different times, depending on the local stellar population and the rate of ionizing photon production. Some regions reionized early due to abundant massive stars. Other regions remained neutral longer. The transition from the cosmic dark ages to the fully ionized cosmic renaissance occurred over a period of several 100 million years, not instantaneously. The cosmic renaissance represented the moment when the universe transformed from a dark, neutral place dominated by invisible dark matter into a luminous universe filled with galaxies, stars, and light. This transition spanned roughly from redshift 30, when the first stars began forming, to redshift 6, when reionization was complete. The universe had been reborn, illuminated by the first sources of light. The early universe became filled with galaxies, each containing billions of stars. The stellar populations dominated the physics. The radiation from stars shaped the intergalactic medium. The supernovae from massive stars polluted space with metals. The energy from stellar feedback regulated how rapidly gas could collapse into galaxies. The cosmic renaissance saw the emergence of complex structure. Galaxies grew by merging with smaller galaxies and by accreting gas from the intergalactic medium. Some galaxies accumulated vast amounts of mass and began to develop central supermassive black holes. The first quasars appeared, powered by accretion onto massive black holes. These quasars shone with luminosities exceeding 1 trillion times the Sun, visible across the entire observable universe. The quasars contributed significantly to the ionization and heating of the intergalactic medium. The universe during this renaissance was far more structured and dynamic than the earlier Dark Ages. Galaxies formed, collided, and merged. Stars formed, lived, and died. The heavy elements produced by stars spread throughout space. The universe was in constant transformation. The cosmic renaissance lasted roughly 1 billion years, from about 200 million years after the Big Bang to about 1 billion years. By the end of this epoch, the universe had achieved the fundamental appearance it retains today. A universe filled with galaxies, stars, and light. The Dark Ages had ended forever. Our own Sun is a population I-star formed from gas, enriched by countless generations of stellar alchemy that began with the very first stars. The Sun is not one of the first stars. It formed about 4.5 billion years ago, when the universe was already 9 billion years old. The Sun's composition reflects this heritage. About 2% of the Sun's mass is composed of elements heavier than helium, what astronomers call metals. This 2% is inherited from every generation of stars that lived and died before the Sun formed. Each star synthesizes heavy elements in its core and returns them to space when it dies. The first stars synthesized the first tiny amounts of carbon, nitrogen, oxygen, silicon, and iron. These were incorporated into the second generation of stars, which synthesized more metals and returned them. This process continued through generation after generation of stars, each one adding to the cosmic inventory of heavy elements. By the time the solar nebula began to collapse, 4.5 billion years ago, the gas from which the Sun formed had been enriched through billions of years of stellar nucleosynthesis. Every carbon atom in the Sun was forged in a star that died before the Sun was born. Every iron atom in the Sun came from a supernova explosion in the early universe. The Sun is literally made of stardust from previous generations. The Sun's existence depended on the first stars having done their work. Without the population 3 stars synthesizing the first metals, the cooling efficiency of gas would have remained poor. The Sun would never have formed. All stars like the Sun owe their existence to the first stars. All planets orbiting such stars depend ultimately on the chemical enrichment that began with the cosmic dawn. Elements comprising human bodies originate in stellar furnaces and cosmic explosions stretching back to the universe's earliest moments. The oxygen in your lungs came from stellar nucleosynthesis. The carbon in your cells was forged in dying stars. The calcium in your bones was created in supernovae. The iron in your blood comes from the iron core collapse of massive stars. Every element in your body heavier than helium was synthesized in a star and released into space when that star died. Many of your body's elements come from multiple different stellar sources. The oxygen might come from a star that lived billions of years ago. The carbon in that same oxygen atom comes from a different star. The iron in your blood might have come from several different supernovae, each contributing some iron to the interstellar gas from which your Sun and solar system eventually formed. You are composed of the ashes of dead stars. Each atom in your body carries within it a history spanning billions of years. The first stars, the population 3 objects, created the very first heavy elements. These elements spread into space and were incorporated into the next generation of stars. That generation created more elements and spread them further. This process repeated through countless generations. Over billions of years, the cosmic inventory of heavy elements grew richer and richer. By the time the Sun formed, enough metals had accumulated to allow planets to form. By the time Earth formed, the conditions existed for life to emerge. By the time your ancestors developed consciousness and looked up at the stars, the entire history of the cosmos was encoded in the very atoms that comprise your body. You are not separate from the universe. You are a physical manifestation of the universe's history. Ongoing mysteries surround the first stars, perplexing questions that observers and theorists continue to grapple with as new observational data emerges. The exact mass distribution of the first population 3 stars remains genuinely uncertain and debated. Were they all extremely massive, exceeding 100 solar masses? Or was there a wider distribution of masses, with some stars being merely very massive rather than extraordinarily massive? The answer depends critically on the cooling mechanisms available in the primordial gas and specific details of how fragmentation proceeded in the collapsing clouds. Current models suggest a wide range of masses was possible, though with a skew toward higher masses, but the most massive stars were definitely more common in the early universe than modern star-forming regions. The contribution of population 3 stars to cosmic reionization remains intensely debated among researchers. Did the first stars alone ionize the universe, or did the second generation of population 2 stars contribute significantly to the ionization process? Did quasars powered by early black holes contribute substantially to reionization? The answer depends on how many ionizing photons were produced per baryon of star-forming gas, and how efficiently the photons escaped from galaxies. Another deep mystery surrounds the nature and origins of the first black holes. Supermassive black holes appear in the centers of galaxies, with some existing when the universe was less than 1 billion years old. How did these black holes grow so massive so quickly? Did they form from population 3 stellar remnants? Did intermediate mass black holes exist as seeds for supermassive black hole growth? The mechanisms by which black holes grow remain incompletely understood and are an active area of research. The role of magnetic fields in the early universe also remains genuinely mysterious. How strong were primordial magnetic fields? How did they evolve over cosmic time? How did they influence star formation and the feedback processes that fundamentally shaped galaxy evolution? Future observations with improved instruments will address these mysteries and reveal new questions. The James Webb Space Telescope continues to discover galaxies and stars at ever earlier epochs. The images from JWST have shown galaxies existing at redshifts exceeding 20, earlier than many models predicted. The upcoming Roman Space Telescope will conduct wide surveys of high redshift galaxies, identifying rare objects that are too faint for JWST to study individually. The Square Kilometre Array, a ground-based radio telescope currently under construction, will detect the 21-centimetre line from neutral hydrogen in the early universe. These observations will map the ionization state of the universe as a function of redshift, showing precisely how reionization progressed. The SK will revolutionize our understanding of cosmic reionization and the properties of the first stars and galaxies. Advanced spectroscopy with future instruments will allow determination of the ionizing photon escape fraction from individual galaxies, crucial for understanding reionization. Detailed studies of extremely metal-poor stars in the local universe will continue to provide indirect evidence about the properties of population 3 stars. New computational techniques will allow simulations of early star formation with increased realism and greater resolution. As observations and simulations improve, a clearer picture of the first stars will emerge. The mysteries that remain will eventually yield to sustained observational and theoretical effort. The legacy of first light extends far beyond the immediate cosmic sunrise. The first stars set in motion a chain of events that led inexorably to the universe we inhabit today. They created the conditions for galaxies to form and grow. They synthesized the chemical elements essential for life. They ionized the universe, transforming it from opaque to transparent. They set the properties of the intergalactic medium that would determine how galaxies evolved for billions of years to come. Without the first stars, the universe would be unimaginably different. It would still be dark, still mostly neutral, still lacking any structure more complex than the largest dark matter halos. It would be a universe where no life could exist, where no observers could look up at the sky and wonder about our origins. The first stars made everything that followed possible. They were the spark that ignited cosmic history. Their light has traveled across 13 billion years to reach us, carrying with it information about a universe in transformation. When we observe the most distant galaxies, we see light that has been traveling since the first galaxies were still young. We are looking back in time to an era when the universe was finding its voice, when the first stars were learning to shine. We are witnessing the universe's childhood, a time of growth and transformation that shapes everything that would come later. Let yourself rest in the wonder of it all, knowing that you carry within you the legacy of these ancient first stars. The light they emitted so long ago traveled through the cosmos and eventually helped build the atoms that make up your body. You are made of first starlight. You are made of the ashes of cosmic dawn. You are a child of the universe's renaissance, born from the very elements those first stars created and scattered into the cosmos. The journey of the first stars does not end in the ancient past. It continues in you, in everything you see, in the ongoing story of the cosmos. Rest now, knowing that you are connected to the entire history of the universe, linked by chemistry and physics to the first moments of light in a once dark cosmos. The story continues. The universe endures, and so do you.